Welcome to this special episode of Frequency Matters, the RF and Microwave Update series. I'm Pat Hindle, and I'm here with my co-host Gary LaRude. Today we are talking with Houman Zarankoub, Senior Wireless Product Manager at MathWorks, and Asi Salarila, Space Segment Manager at MathWorks, about satellite communications and the way that engineering software plays a key role in the advancement of artificial intelligence. There's been a lot of discussion about artificial intelligence and machine learning recently, but what potential does AI have in the space industry, specifically for engineers?
Yeah, it's a great question, Patrick. AI actually has pretty strong potential in the space industry. And one reason for that is that there are several practical applications for AI that can help engineers do their jobs. There's a potential to solve problems that are cropping up that are actually infeasible without AI. I can give you a simple example. Today's space systems are so complex that the amount of data they generate, even just from the testing process, is so large that it's extremely difficult to analyze all of that data, by hand, by human being. So that's one area where the analysis of this big data, AI, machine learning, and deep learning can be really very useful. Another example might be satellite fleet health monitoring. Likewise, you have a ton of data coming down to the ground, limited resources in terms of the people that can analyze it. So AI has already been put to good use there. In terms of the engineers themselves, we're already starting to see engineers adding AI to their skill sets. And I think the marketability of having this skill as an aerospace engineer is only going to increase for the individual. And the capability of being able to deploy AI to make workflows more efficient is going to continue to become more important for corporations and companies.
So we've talked about AI. What trends are driving wireless into the satellite communications area?
Talking to our customers and our thought leaders in the wireless area, I can say that we identified three industry trends that are pushing wireless to the satellite space. One of them is what's known as ubiquitous connectivity. There is an expectation that every device will be at some point connected to internet. And if you want to do that, not only in the areas where with high density of people, but no matter where you are in the world, the expectation is that you want to have same quality of service, same throughput, same performance. And that ubiquitous connectivity is something that affects the expansion of wireless industry into satellite. Number two is essentially cost or financial burden. As you can imagine, the deployment of cellular technology has been rapid in the last 2-3 decades. But if you talk to anybody who knows about that expansion, it has been geared toward high density areas to put base stations in urban areas and along the highways and so on. And the cost of giving the same quality no matter where you are in the world is prohibitively high. And number three, that brings the notion of putting essentially your base stations into orbit a very viable choice. But technologically, the third trend is that with the emergence of this thing called LEO satellite constellations, the low Earth orbit LEO satellites, which enable you to look closer to the ground, which enables you to have higher throughput and performance and speed, that has opened the door for satellite communication to be part of the major wireless push. Of course, technology over there is very difficult because you have to maintain not only one satellite, you have to go from the old geo satellites, geostationary, to LEO and low Earth orbit. They zoom around the Earth. You see them only 5 seconds at any moment. So you have to manage a constellation and all of those technical aspects. But it's these three major reasons, ubiquitous connectivity, cost, and technological advances of LEO satellites, seem to be the trends pushing wireless into satellite area.
So how does engineering software play a key role in the advancement of AI in this industry?
Well, if you think about machine learning and deep learning, they use software by definition, right? The definition of machine learning, which deep learning is a subset of, is that as a computer, it is software training an algorithm as opposed to an engineer doing that, that training using their own expertise. So engineering software is really at the heart of AI when it comes to machine learning and deep learning. And ultimately, I think people are going to start deploying machine learning and deep learning algorithms, not only to enable capabilities that weren't possible before, but also to drive down the cost of development, where the complexity of developing such a system the traditional way would make it prohibitive. And I think up until now, what we've seen is engineering software has been an enabler that's enabled the possibility of using machine learning to even have it be possible. But in the future, I think we're going to start seeing engineering software not only make it possible to start with, but also to make it more efficient and effective by simplifying AI workflows, making those workflows accessible to both data science experts, who are traditionally the machine learning experts, and aerospace experts who have the domain knowledge that's necessary in order to really develop the algorithms that are relevant to the industry. And beyond that, I think we'll also have a growing need for software development platforms that allow a robust validation verification of AI type algorithms. That's an emerging field. It hasn't quite been solved yet, but it's coming along, and I think there's going to be a strong demand for those types of software platforms.
So that's very impressive. Given the potential for these software platforms, what steps should engineers consider when they're developing a satellite communication system?
So technically speaking, when you are embarking on developing satellite communication for wireless, the problem you're addressing is a multi-domain, multidisciplinary problem in nature, meaning that you cannot just rely on a particular kind of discipline as well as a domain of analysis and design to get the task done. Let's just go through some of these multi-domain issues you have to address. Start with an antenna array. More and more, as we develop these LEO satellites close to Earth, fast moving, these satellites, each time they're going to talk to multiple ground stations at the same time. So you need to have lots of beamforming, lots of multi-array processing. And so you have to go toward the MIMO and multi-antenna techniques. So that's one discipline you have to master when you are trying to do the traditional antenna arrays don't work anymore. Number two, and the most important, one of the most important one, the challenge of space exploration as well as satellite communication is essentially the challenge of signal power. As you go further from the Earth, signal power drops precipitously. So your RF module, RF circuitry is in charge together with the antenna array to boost power as much as possible. And you have to maintain the quality. So that RF design and antenna design together becomes a second type of problem you have to solve. Now, these LEO satellites are very fast moving in nature. So based on your even topic of your frequency matters, you know about Doppler. Doppler is a huge problem for fast moving wireless communication systems. So you need some digital signal processing, to counter the effects of Doppler and other constraints on your system. Then you have mechanical design challenges. I told you these LEO satellites move fast and they react to each location by not only turning the beamforming patterns digitally, but also move their body and the gimbal. So we have mechanical design challenges there. Finally, as I mentioned, LEO cannot work with one LEO in the orbit. You have to have a constellation of 500, 1,000, more than that. So you have to have the network design and inter-satellite communication challenges. So just in a very short description, you see how at least 5 different challenges have to be met before a successful LEO satellite constellation can be used for wireless communication.
Yeah, those are a lot of good points, especially the Doppler delay is very long in spacecraft.
Absolutely.
What are the primary challenges for the future of autonomy? What does it look like for spacecrafts, and how are machine learning and deep learning pushing autonomy forward?
Yeah, so I would say autonomy is definitely one of the large mega trends in the space industry. And a lot of what's driving that is the complexity that Houman was alluding to. I see the industry really in the early stages of making a transition from satellites and spacecraft that were under full ground control, like they used to be in the past, to more and more autonomy. If you take the field of deep space exploration, for example, we've over the decades transitioned from flying a spacecraft past a planet to autonomously landing a spacecraft on a planet to now we're at the point where we're flying helicopters on different planets. If you look at the Mars helicopter as an example, and clearly as you progress down these steps, more and more autonomy is required. And part of that is actually it's a very simple communications related reason. The further you get from Earth, the longer it takes your communication signal to go back and forth to your spacecraft. Even at the distance of Mars, it's completely infeasible to joystick a flying helicopter. It takes many, many minutes for the command signals to get to Mars and to come back. So the spacecraft has to be autonomous. And if you look at these LEO constellations, like what Houman was talking about, 10 years ago, a constellation of 10 satellites would have been a large constellation. And as Houman said, now we're talking not out of hundreds of satellites, but thousands of satellites. So the ground control has to scale with this complexity. And it's just not practical to keep adding human operators to control these satellites. There has to be this autonomy as part of that. And also, as we move into the future, there's also a trend towards solving more and more problems on the spacecraft itself that can benefit the mission. There's another example that's also very relevant to wireless communications. That's the example of having an Earth observing satellite that goes around the Earth and it collects pictures or other data of the Earth. Now, if that satellite is trying to image the surface of the Earth, probably half the time it's taking pictures of cloud cover that are not useful for the mission. So wouldn't it be nice if that satellite was able to autonomously detect on board which pictures contain clouds and which pictures actually contain the stuff you want to see and downlink to the Earth, and automatically only send to the ground those pictures that are useful? That would save a tremendous amount of bandwidth. It would really help one of those bottlenecks Houman was talking about of communicating with ground stations and having to manage the bandwidth. So I think the industry is moving in that direction. Those types of applications and solutions that are best solved by machine learning and deep learning techniques are starting to look more and more appealing.
So I'd like to go back, Houman, to the comments that you made about the challenges that engineers need to consider when they're developing a satellite communications system. How can simulated testing help?
As I was thinking about this, I identify 3 elements that represent those challenges, and the simulated testing can really help with that. I call them accuracy, efficiency, and robustness. Let me go through one by one. In terms of accuracy, what LEO satellites and even the next generation of 5G networks, the millimeter wave that's coming in the future, have in common is that we are talking about high center frequencies and very narrow beam widths to communicate simultaneously to multiple users. When you have those beamforming and high frequency technical challenges, there is no margin of error for your localization. That's the problem. If you make a millimeter, centimeter mistake in the localizing your ground station or in the uplink from ground station to satellite, you lose a lot. So accuracy and coming up with designs that have very low margin of error can best be handled through simulated testing, because you go through all possible choices and you find the best choice. That's one element. Number two, I call it efficiency. I told you the ubiquitous connectivity is the goal, right? Everybody in the Earth. And the promise of satellite communication is with these LEO satellite constellations, no matter where you are, even on the mountain in the middle of nowhere, I can give you high throughput. If the design is suboptimal and just by virtue of a cloud or rain or any kind of a distortion, you will lose your performance, then satellite communication cannot emerge as an alternative to established technology. So it is in the best interest of people providing satellite communication to make sure they optimize the design before it goes up in the orbit. That's the efficiency notion. Number three, I call it robustness. Something about satellite communication. If anything goes wrong, you cannot send the astronaut there to fix it. It's just not feasible. So every possible failure mode has to be provisioned and tested before anything goes up in the air, right? I call that robustness requirement. And therefore, you have to anticipate almost all failure modes in your before prototyping the simulation, as well as prototyping stage. When it goes up, that's it, it's final stage. So these are the three elements that I think simulation and testing can help the designers provide accuracy, efficiency, or robustness, which are necessities for satellite communication.
So maybe to wrap it up for both of you, are there any specific considerations for LEO satellites for engineers working in the aerospace and defense industry?
Yeah, so if you look at the AI, machine learning, deep learning realm, LEO is really a rich area for AI because training data is readily accessible from LEO. We're already flying a ton of spacecrafts in LEO orbit. And if you look at the base between the LEO orbit and Earth, with the various obstructions to communications it may have, like Houman alluded to, whether it be clouds, rain, we have a lot of data collected on that. And that's in contrast to, say, something like deep space exploration, where we really don't have a lot of data about, for example, the moons of Jupiter. Certainly not enough to be able to train algorithms like we can train for the LEO environment. So that's really a key thing to keep in mind. There's also, as we talked about earlier, there's a tremendous need for increased autonomy. And I think in low Earth orbit specifically, that autonomy will focus on safe autonomous operations. Things like managing collisions, collision avoidance with other satellites and other constellations, collision avoidance with debris. Any of those types of things could be catastrophic because they only create more debris, and it's kind of a domino effect. So it's very important that we have those safe autonomous operations and a robust control autonomy that can enable that.
On the wireless side, if I want to provide recommendation or considerations for LEO satellite design, I would say that complexity and multi-domain problem that I mentioned earlier, it is affecting the LEO satellite development workflow and the momentum right now. We see a lot of activity in 2020 and 2021 and beyond in LEO because it's emerging as a not only an idealized but a viable alternative for wireless connectivity. And imagine I mentioned to you the multi-domain nature where RF engineer has to optimize their RF design based on modifications to the antenna engineer's work, and the digital guy based on the both of them. So you need a software testing and environment of design that lets you leverage each iteration based on the work of your colleagues, which are not that much well-versed in your domain. So you need a design environment, a platform of design, where all the modification you do in one domain becomes part of the testing of another domain and vice versa. So the design iterations and integration becomes much easier. So therefore, you can go through all those failure modes and design choice explorations that I told you about. So the testing is not an luxury anymore, is a necessity, and you need an environment for testing that enables you to go through design iterations faster and more efficient.
Well, thank you, Aussie and Human, for a really interesting look at the use of AI and engineering software for the space market. As there's a resurgence of development in this area, particularly from commercial ventures and LEO satellite systems, as you noted, this is a timely topic. So we appreciate your sharing with us.
Thank you so much.
And to our viewers, thank you for watching. You can find more interesting videos and interviews at videos.microwavejournal.com. And we'll see you next time on Frequency Matters.